this code can calculate both American option and European option. Therefore, I recommend you to carry this code around so that you can just update number input variable, and then you can get both European option value and then American option value. Okay, import numpy snp usual library numpy library from scipy test input norm, again with the normal distribution, and from typing input literal union optional, we will see that. And then from data class import data classes. Okay, so these are new. Let me explain this code. First, from typing import literal union and optional. Literal specifies that a variable can only have a certain specific values, like in this case option type can be either call or put. Other things are errors. Now union indicates a variable can be one of the several types. So union AB is several type. Union AB is several type. A and B type. Option is the shorthand for union, some type and none. Okay, so it is shorthand for union. And then from data classes, here from data classes import data class. So this is a decorator, so we will put decorator that automatically adds a generated specific method to classes. So once we generate classes, once we generate some special method, automatically add a generated special method to class. Okay, so in the case we will get better understanding after this. Okay, so go down here. Data class. Data class. This is the add data class is decorator. It's called a decorator that automatically adds generated special method to classes again. So class is option parameters. We have a class called option parameters, and we have usual input variable sktRq. They are all float, like real numbers, and they are again current price of underlying values, strike price, time to maturity, risk-free interest rate, and dividend yield and volatility, something like that. So in this way, using like this decorator has many advantages. Reduce the boilerplate code, and automatically create construct and provides a nice string representation and makes the class immutable if specified here, float, and then adds comparison method, something like that. And then we define function posit in itself. It is validate input parameter. So if any not is instance x for x in sktRq, then this is error. Okay, any not is in instance. If they are not, all parameters must be numeric. Okay, all should be numeric. They should be all are number. So instance x or integer, either integer or float. Okay, it is union, either integer or float. If x is less than 0 for x in this asset price, strike price, time to maturity, and sigma, well, they integer for positive, right? Then skt sigma must be positive. If r is less than 0, again error, such that risk-free should not be negative in most cases. Of course, sometimes we have negative interest rate, but in this case, let's exclude that. Okay, exclude that. And then class option pricing class initial self parameter, and the param is option parameter. So we have this input value option parameter, this one. Okay, this one is here as a parameter. Okay, self param, 네, we use the same initialize with validate parameters, and then we calculate d1 d2, and is tuple is a float. Okay, they are float d1 and d2. So d1 and d2 is previously we already saw it, Black-Scholes pricing model. So first we define f is basically again for the price, so it is s is of course self param, so the parameters is this one, but parameters from optional motion parameters, so it is here, something like that. It is connected that way. And then exponential numpy exponential function of again r minus q, interest rate minus dividend yield multiplied by time to maturity. Now you can define d1. d1 is log of f divided by k plus 0.5, and then square power of square of sigma variance, and then time to maturity, and then this one we change line with this one divided by and change line, and then sigma standard deviation, and then root t. d2 is d1 minus sigma root t, and then we return d1 and d2. They are tuple float. Now Black-Scholes is same. Option type is literal. Okay, literal. So it should be either call or put, and then it generates float or real number. So it should be either float or call. So efficient coding. So European option pricing using Black-Scholes formula with improved error handling. Try f is again same for the price as exponential r minus qt, and then b is bond price, right? And then d1 d2 is self calculate d1 d2. We calculate d1 d2 over here, and option type is call. So option price b discount of f norm cdf d1 minus k norm cdf d2. If it is put, else which is put, then we have b is self param k, and f this one, and the return price. Okay, float. Ensure that return type is float, except exception as e. So value error in Black-Scholes calculation is this one, exception as e. Okay. Now this is for European option pricing. For American option pricing, well, there are many methods, but here I will explain most popular way of calculating American option. The most popular one is called binomial tree. In the binomial tree is self, so we import the prior one, and the option type is literal. It can be either call and put, same. And the step is here, default value is 100. If we have a large number, it becomes more and more accurate. Okay, so output is float. American option pricing using the binomial tree method with factorized operation. We use a factor to make efficient code. And then step size should be greater than 1. So if less than 1, number of steps must be positive. And here we get dt is t divided by step. T is time to maturity divided by step, so it is length per step, right? U is important parameter, is exponential of sigma, and then root dt. Again, dt is time of each step. So if we have like very large number here, then it is very short period. T is simply 1 over u. Then P is called risk neutral probability that underlying stock price go up. Is exponential of r minus q dt, and then minus d over u minus d. Okay, so this is famous one. So if not, P is 0 and 1. P is probability, so it is probable, so it is always between 0 and 1. Okay, so if it is not, invalid probability. So sometimes it is less than 0 or greater than 1, but in most of cases it is not. Now discount rate is discount. So discount are discount per step, So R is discount rate and DT is per step discount. Now we do factorized tree calculation, and then J is already step uh, plus 1, and the price is S multiply U step minus J D plus plus. Okay, something like that. D power of J. Okay, J is at the end of the step. Okay, so here the J NP or range steps n plus 1 creates actually array or vector, creates a numpy array of a consecutive integer from 0 to step, the inclusive step. Okay, so terminal pair. So in binomial tree at time t, let's see what's gonna happen. So when option type call, then the option value is price minus maximum of price minus self k0, which means that if this is positive, then this is option value. So if stock price as a price greater than k, people will exercise. So profit, this is instant profit. Otherwise, when people have no reason to buy something at higher price, so if it is negative, it is simply zero. They don't exercise option. Put option is the opposite. At the end, when people exercise, then profit is from selling price and the current price. If it is negative, people won't exercise. Okay. So now we define option value at terminal period at expiration day, but American option, they can exercise option in the middle. So we do backward induction with factorized operation. So for I in range step minus 1, and then we move backward from the bottom, so from the back. So price is the last one and divided by u. Okay, so it is like prices, we fill the numbers here, and continuation value. Okay, continuation value is discount multiplied with discounted p option value and 1 minus your option value. So it either up or down. Okay, up or down. So up or down. So if we don't exercise it, then it can either go up, go down with probably p 1 minus p respectively, and we discount. And the intrinsic value is that it is American. So what's going to happen? We exercise right now. So if it is call option, is price minus price minus exercise price. If option type is call, else it is exercise price minus price. Right? So option value is, if waiting continuation is bigger, then we will not exercise the American option. If it is intrinsic value is larger, we exercise the American option. So we choose between continuation and intrinsic, and we do it layer by layer, grid by grid with this one, and then we get option value 0. Now long stop short one, this is another popular method of calculating American option price. So we have a self, and the option type should be literal call put. It should be either call and put, and simulation, let's say 10,000 simulation. Okay, but of course if we have a larger simulation, then we will get a more accurate number, of course. And the step, also if we have a larger step, this is larger, we will have it's same to American option, we will detail degree integer 2. Okay, so American option pricing using long step short method will improve the regression. Okay, so simulation less than 10,000, number of simulation should be at least 1,000. Well, with this number of simulation, we cannot get a good answer. So we should have a reasonably large number of simulation. Step size 10 is again less for the error. Number of steps should be at least 10. And then degree either 1 or 5. Polynomial degree should be between 1 or 5. Okay, so degree means we are estimating continuation value with some polynomial function. dt is same to the previous binomial tree. Terminal period t divided steps. So if we had more step, larger step, default is 50, then yeah, it goes a shorter and shorter period. So discount factor is for each grid dt, we discount as r, so it is discount factor. Now we can generate passage using antithetic variate for variance reduction. So suppose we want to 10,000 simulation, then it is integer by integer divide. So if it is a 10,000 simulation, actually we do only 10,000, then 10,000 simulation. Actually we only do 5,000 simulation because we are writing efficient code and step. So these are random table of random number, 2D table random number. And remember, even though simulation step 10,000, we need only 5,000 here, because whenever we simulate something like a z, we multiply -1 and regard that as another simulated number. So if our random number produce 0.3, then we think -0.3 is also simulated. So it is a way of saving number of simulation to save computation resource. Also we have balanced simulation. It is actually better. So drift term, we call it drift term. Drift term is called r minus q minus 0.5 self parameter sigma square root c. Okay, so it is called expected return. Okay, expected with a log return, something like that, intuitively. And the diffusion is self param sigma, so it is diffusion factor, so it is volatility per period, which is dt. Now simulated path with factorized operator. Asset path with simulation, and the step +1. Okay, first we have zeros, and asset path. First one is self parameter s. At the very first column, so it is scenario of underlying asset, but all start from the current stock price. So it is starting value, it is s, and in range you want to step s. So for each row, we generate SFS such that t SF value at t is starts from t-1, and then because when 0 we already know the value, something like this. Okay, and then we drift and diffusion, we add expected return, and then we add risk. Okay, we add risk, and then calculate intrinsic value. Option type is called intrinsic value is of course asset path price minus k exercise price, and then for put option is k exercise price minus s. Now intrinsic option value at the maturity, because we don't have any waiting option end there, so this intrinsic value is option value at the end. However, in the backward induction it is not so, because we have either intrinsic value or we can wait. Okay, so steps in the money, intrinsic is greater than 0 is called in the money. If NP sum in the money is greater than degree +1, ensure enough points to regression. Okay, enough points to regression, so that x is asset path in the money and y is option value in the money. Okay, and the discount. So well, x is asset path and then y is the option value. So we have this is asset value and then option value, and then we match y with the function of x. Basis is NP column stack is x I to the range degree 1. So it is the basis function 1 x square. X is asset path, and then we match try beta is NP linear algebra basis and y, right? Match, and the conditional value is this basis and beta. Okay, because we do linear algebra, and then we span y option value with combination of power of s. Basically, that's the idea. The exercise is intrinsic value in the money is greater than continuation value, which is from this one, from the regression, linear algebra. Then we exercise other not. So option value in the money is empirical exercise. So if intrinsic value is big, this one otherwise is option value. It's a continuation value. Except some error term. Okay? This is error term. Except MP linear value link error. So fall back to simpler regression. If numerical issue occurs, then we use very simple second order regression. Okay, very simple regression. And continuation value is the very simple polynomial valuation, and the exercise price is between the two. We determine exercise whether it is better to wait or not, and the option value something like that. And the option value is in the money and discount. Okay, we discount and in the money, and the return for NP mean option value and the discount. Okay. Now example usage with improved error handling. Okay. Let's say current stock price 100, exercise 110, time to maturity 1.5, risk free rate 5%, dividend 2%, and volatility 40%, and option. We define option pricing parameter option, initialize the pricing model, and calculate price with all method. European call option, black short, option black short, and call, put, and then step size. This is binomial, and then long stop short, something like that. Using this option. Okay, so this option is using this option with black short. So this is like black short is determined here. So given the option, yeah, we have black short. Where is it? Well, I know it is possibly complicated if it is new. Python is new to you. And then we actually print out value. Option pricing result. Okay, print. So first we get the line, and then yeah, we print out and then plus up to the fourth digit. And then option pricing result is European call option price $16.8588. European put option is this one. And then American call option price is 16.8. So, well, American call is lower than this one. Okay, it doesn't matter. This always should higher than this one, but there is possibly numerical error. This is actually better. This is higher. And put option price, European put option is this one, and the American put option price should be higher than this one. Yes, it is higher. A long stop short algorithm. This is the value.